to everyone. So now we are very close to our board exam. So you all must be very much, little bit tensed about it, how we can approach the examination, because most of you might have prepared your syllabus completely by the time, because pre-final is about to start, and some of you might have little prepared, some of you might have not prepared at all. But forget about the past. It is a time that we have to think how we can make use of the coming few days, and which is very valuable for us. And at any cost, we are not going to quit our exam. We are going to face what we are going to get the exam. Okay, for that, I'm going to give you some important tips. For example, in physics, and I focus on my subject especially, that physics, and I will tell you how to plan out your learning pattern in short time. Okay, for that, first of all, I tell you, you have to study the entire syllabus. So here I am giving you a thing called priority learning. That means when the exam comes, from the previous year's papers, when you go through, we can see some repeated questions which make us at least 80%, because for our coming future tenure, for any qualifying test for higher studies, when you go your 12th standard, you need minimum 75 to 80%. For example, DASA quota, when you enter into NITs, National Institute of Technology, these places and all, minimum score we require, I think 75%. So our target is not just passing, our target should be just getting at least 80% in the forthcoming board exam. And don't lose your heart. First of all, develop your confidence and fix your goal and take a strong determination that the coming days we are going to make use very, very critically and very sincerely by 24 hours hard working, and definitely you can make it. This is what I'm going to tell you. So first of all, let us see about, if you're talking about physics, okay? First thing, don't leave any MCQ questions. At any cost, don't leave any MCQ question. Secondly, attempt all the questions in this paper. Attempt all the questions. So first we have to focus on 5-mark questions. These 5-mark questions are usually, one part will be, most of the time you can see from the previous papers, it is a part sort of derivation plus a numerical. So this area we should cover very clearly. Then 15 mark we can take in our hand. Then next we are going to see MCQs. MCQs also, if you concentrate a little work onto it, definitely can get out of 18 question. Out of 18 question, you can just get around 12 mark easily. You can clear it. Okay, so don't leave any MCQs, even though you don't know. Just think of the probability. First of all, you strike off the questions which are not sure to you. Which are not answer at all. Because when we read 4 options, we can make sure that which are not at all the answers. Let's strike it off. Then we are doubtful about just 2 bits, 2 options. So there you can choose 50-50 chances. So naturally, we may probability 50% we may get it. So don't quit any answers. First thing. Then secondly, let us see chapter wise. Okay, take an easy chapter which you like most. Example, if you are taking physics, semiconductor, I feel it is the latest one we completed. Last chapter we finished. So you all must be very familiar to this chapter, and you might have prepared well this chapter. And it's very small chapter, and it is a weightage of around 7 mark. So within very small area, if you cover 7 mark easily you can score. So first I will start your topic with semiconductor devices. Okay. So usually the expected area that we have to cover is energy band diagrams. We know in energy band diagram, 3 types of materials are classified using energy band diagram. First one, insulator. Second thing, conductors. Third one, semiconductor. Let us have a brief idea what are the difference it means. Again, for example, energy band diagram is a diagram or is a graph in which energy is plotted along y-axis and interatomic distance plotted along x-axis. So usually this area we are not marking anything, but that's actually, if you want, you can mark it as interatomic distances. Okay. So here, when we speak about different levels, say insulators we are taking, it's outermost level when we are marking here, because usually in interaction between atoms, outermost shell we have to consider, because innermost shells are not affected by external effects. So what we do, first we mark this is valence band. When we speak about valence band, this is the energy level of outermost shell of an atom. Electrons in the outermost shell of the atom. Okay? So here, this valence band, this outermost shell of the atom, see, it is in the case of insulators, energy level is very, very low. But we know for conduction, energy level should be very high. Okay? For conduction. So actually, what's the meaning of this valence band? When we say electrons are in valence band, it means this electron just moving around the nucleus. So that is associated with an atom itself. When we speak that electrons are in conduction band, that means it gains some energy from external agents like heat or light or something. It gains some energy and go to higher energy level, so that it can go from one atom to another atom. This is happening in metals. This is called conduction band. So when we speak about valence band, remember that you are speaking about electrons which are moving just around the nucleus. But when we speak about conduction band, electrons are able to move from atom to atom throughout that material. Within the material it can move throughout. This is the meaning of conduction band, or energy which is in the conduction band. So here, when we take an insulator, all electrons are completely moving around the nucleus. So if we connect a battery, there are no free electrons. They cannot make any kind of conduction. Electrons are moving only around the nucleus. So we can say complete electrons are in valence band. Conduction band is empty. Therefore, if you connect a battery, it's not going to conduct. So in short, we can say in insulator, valence band has energy very, very low. But there is a 6 electron volt to 7 electron volt is the forbidden energy gap. This E suffix G represent forbidden energy gap. So forbidden energy gap between valence band and conduction band in an insulator is very, very large. That's what it cannot conduct electrons very easily. So it is categorized as insulators. So we can say insulators, valence band is very, very low. Energy gap between valence band and conduction band is 6 electron volt to 7 electron volt. If we speak about metals, for example, copper, aluminium, gold, these kind of materials, atomic number say ferrum 26, or gold if you are taking 79, this is atomic number. So if you mark it 2, 4, 8, 2, 8, 18, 32, like that, if you are filling the shell, then you can see this is the conduction band. That is always constant. This is the conduction band. Electron gains its energy can conduct. Now valence band, if you are marking first shell, second shell, third shell, fourth shell, like that. In metals, if you are taking valence band, it will automatically come to this layer which is equal to conduction band. So we don't have to supply any energy. By nature itself, its outermost shell has an energy. That means valence band energy is overlapping with conduction band energy. Therefore, for conduction it's very easy, just connect a battery. Electrons are largely available in the conduction band because by nature itself, its outermost shell, that's valence band energy, is equal to conduction energy. So it can easily conduct within the material. So we can say valence band and conduction band are overlapping. So again I repeat, in insulators, energy gap between valence band and conduction band is 6 electron volt to 7 electron volt. But in the case of metals, valence band and conduction band are overlapping. Okay, so electrons are largely available for conduction. So this behaves as a conductor. So third case we are speaking about semiconductor, which is our main focus in this chapter. In semiconductor, for example, 14th group element, germanium and silicon. In germanium and silicon, see valence conduction band is again the same level. See everywhere conduction band is same. But 14th group element. 14th group elements means atomic number is 14. So we can accommodate electrons like 2, 8, 4. Total 14. So outermost shell, see 2, 8, 4. So almost here it will come. The conduction valence band will come somewhere here. So if you are taking silicon, this energy gap EG will be around 1.1 electron volt. If I take germanium, this gap will be around, for germanium that will be around 0.8 electron volt. 1.1 electron volt and 0.8 electron volt approximately. So in the case of semiconductor, when we consider, there are 14th group element. Example, germanium and silicon. In the case of silicon, forbidden energy gap will be 1.1 electron volt, and forbidden energy gap of germanium is 0.7 electron volt. Okay, so this is a very small gap, right? So here what happens when the temperature increases, 0 Kelvin, conduction band is completely empty and valence band is full. Okay, this time no electrons in the conduction band. If you connect a battery, it won't conduct. So here, as the temperature increasing, more and more electrons will reach conduction band, leaving hole in the valence band. So here, number of electrons available is increasing. So what happened? Conductivity increasing. So we can say as the temperature increases, in semiconductor, it will behave like a conductor. So it has both the property. At low temperature, they behave like an insulator. Higher temperature, they behave like a conductor. That's why they got the name semiconductors. So here, carbon also belonging to this 14th group element. But forbidden energy gap of carbon is more than 3 electron volt. So what happened? They are almost behaving like a insulator. That's why carbon is not acting as a semiconductor. So in short, we can say insulator are the materials in which valence band and conduction band energy gap between them is 6 electron volt to 7 electron volt, and they do not conduct electricity. In conductors, valence band is overlapping with the conduction band, so large number of electrons are available in the conduction band, so they are now basically conductors. Here in semiconductors, for a valence band comes very close to conduction band. For germanium it is 1. For silicon it is 1.1 electron volt. For germanium it is 0.7 electron volt. So when the temperature increases, they behave like a conductor. This is a basic idea of this one, energy band diagram. So question from here can be asked: draw energy band diagram for conductors, insulators and semiconductors, or any specifically one material they can ask. So this is the way how to explain it. Okay. Second thing, explain why in metals conductivity decreases or resistivity increases on heating, while in semiconductors conductivity increasing on heating or resistivity decrease on heating. The reason in metals, so this is very frequently asked question in the board. That means in metals, as the temperature increasing, resistance increasing, at the same time conductivity decreasing, because there are large number of electrons already available there. So if we increase the temperature, instead of helping for conduction, they collide each other. When they are colliding, they cannot move forward. So in that case, conductivity will reduce, resistivity will increase. For this formula we have used rho is equal to m divided by ne square tau. You all know tau is relaxation time. As the temperature increases, relaxation time decreases, resistivity increases, conductivity decreases. This is happening in metals. At the same time, in semiconductors, no electrons are available in conduction band initially. As the temperature increasing, more and more electrons will reach conduction band and help for conduction. Therefore, conductivity will increase, temperature will decrease. So when we speak about conductors, we have to use this formula and explain in terms of relaxation time. When we speak about semiconductors, we have to explain conductivity in terms of energy gap. So this is about which one? Energy level diagrams. Okay, so this is one question, expected question from this chapter. Second thing, intrinsic semiconductor. Second heading, intrinsic semiconductor. So question can be asked, what is meant by an intrinsic semiconductor? Okay, intrinsic semiconductor history. So for example, silicon. I told you it has 14 electrons in it. 2, 4, 2, 8, 4. Outermost shell has 4 electrons. So we can mark here silicon. See, 4 electrons in its outermost shell. So roughly we can mark like this, see, 4 electrons. I am talking about intrinsic semiconductor. So meaning of intrinsic semiconductor, it's a pure semiconductor. Silicon and germanium are example of pure semiconductor. So we can mark its crystal structure, silicon with the 4 outermost electrons only we are marking here. Easy, silicon like this, 4 electrons. Here all these electrons form covalent bond with the neighboring silicon atoms. Okay, so they form octet structure in its outermost shell and acquire stability. See here what happens. They will ask, along with this intrinsic semiconductor, you have to explain the energy band diagram also. So you have to mark here energy band diagram along with this diagram. That is here energy, your valence band. This is conduction band, valence band and conduction band. For silicon, you can take example. Then 1.1 electron volt is the formulated energy cap for silicon. Here what happens? When we increase the temperature, okay, when we increase the temperature, electron in the silicon gain some energy, go to conduction band. So when they go to conduction band, see they can move all around the material. So the absence there, that's called hole. Here one absence of electron come, that's called hole. Okay, so here what we develop, one electron and one hole developed. These charge carriers are known as intrinsic charge carriers. Intrinsic charge carriers. Intrinsic charge carriers. So as the temperature increases, more and more electrons will go to conduction band, producing holes in the valence band. Now if you connect a battery, then we can see there's a conduction. That means electrons will move through the conduction band. When electron move here, current is in this direction. This is due to conduction of electrons. But at the same time, see here you can see electrons are moving through the holes. Here also see one electron, one hole. Here also one electron come here, one hole producing. So electron can travel through these holes also. The current which is traveling through these holes is known as hole current. So that's also in the same direction. So in a metal we have only current flow only through electrons. But in semiconductor there are two types of electron flow. One directly just like in a conductor, second one through the holes. Okay, so this is, we can write I is equal to IE plus IH. And number of electrons is equal to number of holes. This is also known as intrinsic charge carriers, N. Okay, around 10 to the power 15 free electrons will come at normal temperature if you take 1 meter cubed of silicon material. So this is about intrinsic charge carriers. You have to explain with the diagram and which one this energy band diagram. Next one, how doping. What's the meaning of doping? That's also another important question. What is doping? Doping means it is a process of adding an impurity, suitable impurity into this intrinsic semiconductor so that conductivity can be largely increased. Okay? So here, when we speak about doping, two types of doping possible. Okay? With the pentavalent impurity we can dope it and trivalent impurity we can dope it. Accordingly, we can get two types of semiconductor. After doping, this semiconductor is known as extrinsic semiconductor. So again I am writing here intrinsic semiconductor, silicon. See here, same like before, we have to mark silicon. This I am speaking about extrinsic semiconductor after doping. So doping is a phenomenon of adding an impurity so that conductivity of intrinsic semiconductor can be increased. This process is known as doping. So here is an example of extrinsic semiconductor, silicon with 4 electrons. They form covalent bond with the neighbors. Okay. This time we are taking phosphorus or antimony or bismuth, 15th group element. They have 15 electrons in its outermost shell. So what we are going to do, we are going to add this 15th group element, anything, phosphorus, bismuth, antimony, anything. I am taking a phosphorus adding here. So what happened? Outermost shell, 15th group means 15 electrons are there. So 2, 8, 5. But silicon has last number 4. But when you are putting this phosphorus here, see 4 electrons will form bond with neighboring silicon atom. These silicon atoms are known as host atoms. And 1 electron left without a bond. Okay, this is called donated electrons. donated electron. At the same time, this impurity is known as donor impurity. So energy level of this donor electrons are coming just below conduction band. So what happened? Each doping donates one electron. Around 10 to the power 22 doping usually we make in normal formation of this kind of extrinsic semiconductor. So a large number of electrons will develop here. This energy level will be 0.01 electron volt. So here the question, explain the formation of extrinsic semiconductor. So here we are saying first we are talking about N-type extrinsic semiconductor. Again I repeat, extrinsic semiconductor means conductivity of an intrinsic semiconductor can be increased by doping an impurity into it. Two types of then we get a semiconductor that's called extrinsic semiconductor. Two types of extrinsic semiconductors are there, N-type extrinsic semiconductor and P-type extrinsic semiconductor. Now I am talking about N-type extrinsic semiconductor. In N-type, we are adding one impurity, pentavalent impurity, that is phosphorus, that donates one electron and energy level comes just below conduction band. Now here, electrons are available from here to here. So 1.1 electron volt energy is not required here. Here we need just 0.01 electron volt so that it will come to conduction band and help for conduction. This is the way conductivity can be increased. Here, what happens here? Number of electrons are increasing, but number of holes remain same here almost, right? But actually, number of holes effectively we can see it will decrease. That I will explain in a numerical. So this is very important question. How can we produce a N-type semiconductor? So how can we produce an N-type semiconductor? By doping a pentavalent impurity into it, we can produce a N-type semiconductor. And after doping, one electron will be left free without a bond. The energy level comes just below conduction band and helps for conduction. So like that, large number of electrons will produce. So material will be now like this. Okay, this is donated impurity, that is phosphorus. Okay, this donor atom that donates one electron. This rectangle shows silicon material. In that, every doping donates one electron. So it will be like this. So here you can observe this completely neutral. But now if you connect a battery, there are some intrinsic charge carriers before doping itself, it's available. That you must be taken care. So when we connect, mainly electron flow through electrons, not through holes. So here we can say these electrons are majority charge carriers. Okay, electrons are majority charge carriers, holes are minority carriers. Here, since electrons are majority carriers, we call it N-type semiconductor. So remember, in N-type semiconductor, electrons are majority carriers, but they are electrically neutral because every silicon atoms are neutral, every phosphorus also neutral. So effectively, the entire system is electrically neutral. Here, N is very greater than NH. Okay, so this is the way N-type semiconductors develop. At the same time, how can you make a P-type semiconductor? In P-type semiconductor, we are using a trivalent impurity like indium, gallium, aluminum, etc. Rapidly aluminum. See what happened? Trivalent impurity has only 3 electrons in outermost shell. They need one more electron to form its 4th bond. So they snatch away one electron from neighboring silicon atom. So holes are developing with silicon atom. So every impurity is called accepted impurity. So every impurity receive one electron producing a hole with silicon atom. So here what happens? Same way we have to draw this energy band diagram. This is 1 point electron volt. This trivalent impurity, aluminum or indium or gallium, whatever they are taking, its energy level just above the valence band. Here, this is doping. It requires one electron. That electron will go from valence band of silicon. So this will become negative ion, holes will produce here. So each introduction will produce negative ion, holes will produce here. So each introduction will produce hole here. Each introduction will produce hole here. See, like this. Okay. So here the material here it will be like this. Doped one is required one electron that will take from silicon become negative, hole with the silicon. So it will produce large number of holes, but there are few holes and electrons are there. that's intrinsic charge carriers. So here if you connect the battery, mainly current is flowing through holes. Clear? So this is known as P-type semiconductor. Here majority charge carriers are holes, hence it's called P-type semiconductor. Okay? So here electron flow through holes. Here NH is very greater than NE. So these are the main question can be asked from here. First of all, I told you what is meant by intrinsic semiconductor, draw its energy band diagram. Second thing, we can speak about extrinsic semiconductor. There are two types, N-type and P-type. Explain the way I explained here and draw energy band diagram for two type of semiconductors. This can be a 3-mark question or 5-mark question. Okay. Now from here, expected numerical. Textbook, there's a numerical comes. For example, number of intrinsic charge carriers are given as 5 into 10 to the power 28 atoms per meter cubed of silicon. And doping concentration is 1 ppm, particle per million. That means 10 to the power 6 atoms. So in this silicon cube, 10 to the power 6 atoms, one doping will take place. So total number of doping possible, 5 into 10 to the power 28 divided by 10 to the power 10 to the power 6. So you will get 5 into 10 to the power 22 groups we can get from here. That means in 1 meter cubed material, 5 into 10 to the power 28 atoms are available. In that we are making a group of 10 to the power 6, 10 to the power 6, 10 to the power 6, 10 to the power 6 like that. That means 5 into 10 to the power 28 divided by 10 to the power 6. We will get 5 into 10 to the power 22 groups here. Each group donating, topping with 1 electron, they donate 1 electron. So total 5 into 10 to the power 22 dopings are possible. Each doping donates 1 electron. So after doping, number of electrons available is 5 into 10 to the power 22 electrons will be available. At the same time, 1.5 into 10 to the power, that number, this is an example problem in textbook. So you can take that page number. In the new book, that page number 477. So intrinsic charge carriers are, it's given 1.5 into 10 to the power 60. These are the number of atoms in intrinsic charge carriers. Number of electrons in holes. They are equal in number. So here the formula Ni² is equal to Ne into NH. For example, if there are 100 electrons and 100 protons before doping, after doping, if this becomes 1000, this becomes 10. That means this formula should be maintained for its equilibrium condition. So here what we can do, Ni² is equal to Ne into NH. So Ni² is 1.5 into 10 to the power 16. 1.5 into 10 to the power 16. Number of electrons now you got 5 into 10 to the power 22. From here number of holes also you can calculate. So initially number of holes was this. Now we can see number of holes is largely decreasing. Number of electrons is largely increasing. So in that example question can be asked on the board, and they may ask what kind of extrinsic semiconductor formed. It is N-type semiconductor formed. Okay, so this is about the P-type and N-type semiconductors. Now, how a p-n junction formed? This is another important 3-mark question. Explain how a p-n junction can be formed. P-n junction can be obtained. So it's very simple. We can say that this is one p region. With the diagram we can explain. Here there are two regions. One is P-type silicon, another is N-type silicon. P-type silicon we know holds negative ion, holds negative ion. This is P-type semiconductor. Okay, this is P-type semiconductor. This is N-type. Electrons are majority charge carriers. Electrons are majority charge carriers. But remember, there are some electrons and holes. Before doping itself, it's available. Now, when we join them, due to high electron concentration, electron diffuse into P region. Then when electron diffusing from N to P, current is from P to N. This is called diffusion current. Diffusion current. So direction of diffusion current from P to N. After diffusion, these electrons combine with the holes. When they combine with the holes, what happens? There's a region is forming which is depleted of free charges. See this region, no charges develop. So here there is an electric field developed. This combination continues and electric field here is increasing. We know when an electric field increasing, this electron cannot go in the direction of electric field. Always the electron move opposite to the electric field. So what happened? Further diffusion will be slowing down because the electric field is becoming stronger and stronger. So what happened? This electric field pull the electron back. So that flow of electron from P to N causes a drift current from N to P. So this is drift current from N to P. So actually what's happening? Due to high concentration of electrons in N region, electrons diffuse into P region. This causes a diffusion current from P to N. At the junction, these electron holes are combining. Therefore, electric field is increasing. This will increase until here a potential barrier develop that is around 0.7 volt. This much voltage will develop. Until then, this electron flow will continue. Electric field will increase. This electric field makes electron to come back opposite to the electric field. That causes a drift current, flow of electrons in the direction of opposite to the direction of electric field, or under the influence of electric field we can call drift current. So finally what happened? From here diffusion current pulls the electron forward, drift current pulls the electron this side. So these two will become equal. So this will come to an equilibrium, thus the p-n junction is formed. So when you explain, like a very simple way, when a p region and n region are joined, due to high electron concentration, electron flow from P to N and holes move from N to P. Sorry, electron move from N to P and holes move from P to N. And at the junction, they join. When an electron is moving from N to P, that causes a diffusion current from P to N. Due to electric field, electron come back from P to N. That's calling drift current. That's causing a drift current from N to P. Finally, this diffusion current, drift current are equal, a p-n junction is formed. This is 3-mark expected question. It's given in the note, we note thoroughly, briefly we gave the note, in the notebook it's given. Then here, this is an important question. Now, forward biasing and reverse biasing, that's another important question. Explain forward biasing and reverse biasing. Actually here, we are connecting positive to positive, negative to negative. So this positive develop positive here, this negative. We know this electron is unable to cross here because of this electric field. If we can make this electric field weaker, then electron can go from here to here. This positive comes, that will produce an electric field in this direction, net electric field will decrease. This time this becomes 0.6 volt. Then again, see I am giving 0.1, this becomes 0.6. This I am giving 0.2, this becomes 0.5. This I am giving 0.3, this voltage will become 0.7. So like that, when around 0.5 volt when you reach, this becomes 0.2. This time you can say small electron flowing across here. If you connect a milliammeter here, you can say that's a current flow. So here, once it reaches 0.7 volt, this is completely zero, complete electron will flow like in a conductor. Okay, so here, textbook diagram is given this way. Textbook, this explained, this question asked in textbook. After that, I'll tell you page number. I'll tell you the page number. Yeah, page number 481. This question is asked with the diagram and the graph. So, diagram is this. Instead of explaining this way, this is a symbol of the diode. Okay, this is connected with P to P, N to N. This is N. Okay, then this is showing there is a variable cell. I can change this voltages. This time current will flow is forward biased. To measure it, we have to connect a milliammeter here. We can connect a voltmeter parallel to it. And here, this is a graph. Okay, this is a graph forward characteristic. This is reverse characteristic. Reverse characteristic diagram will be like this. Here, it will be coming like this. Okay, see, same this one, but polarity of cell is reverse. Negative, positive. Here it is marked. This is microampere because only minority carriers are flowing. This is voltmeter. We are connected. This is the way we got to mark. So this is forward characteristic. This is reverse characteristic. I told you page number 481. Clearly it's written. You have to mark it here in milliampere. Here it is microampere. All this you have to mark. Okay, so this diagram, these two diagrams and this graph an expected 3-mark question. So we can say this is the reason for it. In forward biasing, positive connect to B, negative connect to N. So your electric field decreases. For smaller voltages, we can say current start increasing here, and when this voltage is high enough, this depletion layer becomes 0. So your expected 1-mark questions are there. During forward biasing, what happened to potential barrier? We can say potential barrier decrease. I told you 0.7, 0.6, 0.5 like that, and depletion layer becoming thin. This happening. In reverse biasing, what happens? We are changing the battery, same like that diagram. Negative to positive, positive to negative. This time, this is positive, this is negative. Electric field is increasing in this direction. So that pull the electron opposite to that. So depletion layer becomes wider. This value becomes 0.8, 0.9. It increases. So now there is no chance of electron flow here. But we know there are few minority carriers. Now this electron will go. Electrons, free electrons here. Intrinsic charge carriers. Before doping itself, they are available here and here. Now this electron will move opposite to the electric field. Causes a very minute current in microamperes. Around 1 microampere current will form here approximately. Then once it becomes very high voltage, somewhere around 50 volt and all, you can see they start tearing. Electric field will be very strong enough here. Electric field is very strong. They start tearing the electrons from this silicon. That means host atom, and large number of electrons quickly flow from P to N, causing a current from N to P. So that's what say here. So this is not obeying Ohm's law, therefore it is known as non-ohmic material. So your expected question, 3-mark question I told you. Explain forward biasing and reverse biasing with the support of this characteristic. This is called characteristic of graph. So page number 481, the diagrams are there. Using that, if you are writing 3-mark, you will be getting. 1-mark question I am getting from here. During forward biasing, what happened to potential barrier? What happened to depletion layer? During reverse biasing, what happened to potential barrier? Potential barrier increasing, depletion layer become wide now. So these are the important questions you may get from this area. Now, last we are going to the what is the function of this diode? So here basically we understood diode, when it is forward biased, one side current is flowing. When it is reverse biased, opposite side current will not flow. Okay, only one side current will flow. In a normal conductor, when we connect the battery, both side conductor can flow, current can flow. Whatever be the battery connection, any side current can flow. It is just like in a valve. Say for example, a pipe, if you are taking a valve, you connect, one side water will flow, opposite side water will not flow. Similarly, in electrical circuit, in an ordinary conductor, current will flow both sides. But if you connect a diode, current will flow only to one side when it is forward biased, opposite side current will not flow. So forward biasing, current will flow, reverse biasing, current will not flow. So it can act like a valve, it maintains a unidirectional current. One more question can be asked, what's the function of diode? It maintains a unidirectional current, only one side current will flow. Then next important question can be asked from here, page number 482, there's a numerical is there. Okay, in that numerical you can see this approximate way I can mark here. This is a numerical they marked here. Like this. This is forward biasing, this is reverse biasing. Here 10 mark 50 and this is milliampere, this is 20. This side it is marked minus 10 volt. Here 1 microampere is marked. Microampere is milliampere. It's marked. And the question, calculate resistance when diode is forward biased. When current is 15, that means you should not use 15. Above 15.5, below 15.5. That means here you have to go, here you can go. In the diagram, if you check in textbook, you can see here two lines will come. This is 0.7 volt, this is 0.8 volt. So from here we get this is delta V, this is delta I. So if you are taking reciprocal of the slope, what is slope? Slope is equal to opposite side, that is delta I, adjacent side delta V. This is slope. But resistance we get delta V by delta I. For that we have to take 1 by slope. Here what is delta V? 0.8 minus 0.7, that is 0.1 volt. Delta I 20 minus 10, that is 10 milliampere. So we can get here 0.1 divided by 10 into 10 to the power minus 3. This 10 to the power minus 3 will go to numerator. 0.1 into 10 to the power minus 3 become 10 to the power 3 divided by 10. Because this 100 divided by 10, then you get 10 ohm. So here we understood this diode in this case, 10 ohm when it is forward biased. When it is reverse biased, same way, R is equal to delta V is 10. Delta I is 1 microampere, 10 to the power, this is 1 microampere, 1. This is 10 to the power, delta V is, here, delta V is 10, delta I is 1 microampere, 1 into 10 to the power minus 7, which is going to the numerator, 10 into 10 to the power micro, 10 to the power minus 6. So when you go to numerator, 10 into 10 to the power 6, so answer will come 10 to the power 7 ohm. So here, question can be asked, when diode is forward biased, its resistance is in the order of ohm, 10 ohm, 4 ohm, 5 ohm like that. When it is in reverse bias, that is in mega ohm. This can be written as 10 into 10 to the power 6 ohm or 10 mega ohm. So very high resistance. But for an ideal diode, in forward biasing, there is zero resistance. In reverse biasing, there should be infinite resistance for an ideal diode. But ideal diode, we cannot get it. So here we can see when it is forward biased, it's 10 ohm. Comparatively, it is very small. Then when it's reverse biasing, it is 10 mega ohm or 10 to the power 7 ohm. That means here, forward biasing of the order of ohm. Question can be asked. What is the order of resistance when this diode is forward biased? So ohm, mega ohm, kilo ohm, like that they will give. So you should know it is ohm, of the order of ohm. But in reverse biasing, what's the order of ohm they are asking? You have to write in mega ohm. So these are the questions usually come from here. Then another question they will ask. Look here, a diode will be given here. Diode. And this is positive 10 volt. Here there is a resistance, this is ground. Ground means 0 volt. Whether diode is forward biased or reverse biased. We know positive should connect to higher voltage. Means positive to positive, negative term. This is negative N. It's not negative, N region. P region should connect to positive, N region should connect to negative. Here negative in the sense lower voltage we can say negative, higher voltage we can say positive. So P connecting to positive. See higher voltage, 0 volt ground. So this will connect. If you are connecting reverse, this is 0 volt and this is plus 10 volt, then diode will not connect because high voltage to low voltage will current will flow. This is low voltage to high voltage. Or we can say here 0 can be taken as negative. Similarly, if I am marking, this is minus 10, minus 10. This is minus 20. Minus 20. So minus 20 is lower, minus 10 is higher comparatively. Then again it will conduct. This is higher voltage can be taken as positive. Another example, if we say like this, easy, like this also they can ask. Here it is 0 volt, here it is minus 10 volt. So naturally P connected to 0 volt means higher voltage. So P to P, higher volt. This is negative, higher to lower current will flow. This is again forward bias. So this kind of question can be asked. Any diagram will be given. They will ask which, when is it forward biased or reverse biased. So these are the type of question can be asked from here. Next one, we can go with here applications. Rectifier. So rectifier is a device used to convert AC into DC. There are two types of rectifier: half wave rectifier and full wave rectifier. Okay, so here we know usually rectifier consists of a transformer. There is a transformer here. This is a symbol of transformer. This is primary and secondary. This is connected with our supply voltage AC. AC is indicating by this. This is plus AC voltage. You know the property of AC. When generator turns 0 to 180, current will be flowing in one direction, and 180 to 360, current will be flowing in opposite direction. So for example, in this cycle, generator is flowing 0 to 180. This time upper terminal will be positive, lower terminal will be negative. In lower cycle, negative cycle, generator rotating 180 to 360, this time current will flow opposite from here. First current flow this way, then current flow opposite. Then this become positive, this become negative. So remember, we can say during positive cycle, upper will be positive, lower will be negative. During negative cycle, upper will be negative, lower will be positive. Here, connected diode, and here there is a resistance. This is RL, load resistance. This is AC source, this is transformer, this is a diode, this is a load resistance. Now, graph which represent input voltage, V input is equal to, this is a graph, okay, time. Next one, V output VD, right? V output. V output if you are taking, look here, during positive cycle, upper end is positive, lower end is negative. So this end is positive, this end is negative. Diode is forward biased, current will flow, a voltage will develop, that is V output. So we will get this one. During negative cycle, this become positive, this become negative. End B become positive, end A become negative. This time current will not flow. Diode is reverse biased. Then current will not flow, there is a gap. Again when this is positive, this is negative, current will flow. Like that every half cycles will get an output. Here important question, if the frequency of the input is 50 Hz, what's the frequency of the output? That's again 50 Hz, because in this region there is no voltage is developing. Now if you want to make it a full wave rectifier, connect one more diode here, and this one you have to replace it. Now this transformer is known as center tap transformer. If it is 1000 turns, exactly 5 turns, we take a line. So here we can take output. Here during positive cycle, upper end is positive, lower end is negative. So this diode will conduct, current will flow, V is equal to IRL. So we get this output. When upper end is negative, lower end is positive, then this diode D2 is forward biased. Then again current will flow in the same direction, and you get output here also. Like that every segment you will get output. Here what happened, if this is 50 Hz, frequency will be 100 Hz. So this is very important, very frequently asked question. When input frequency 50 in half wave rectifier, output 50 itself. When input is 50 Hz, in full wave rectifier it is 100 Hz. Now this pulsating DC, if you give to a filter circuit like this, it's a filter circuit, then XL is equal to 2 pi FL, XC is equal to 1 by 2 pi FC. Here voltage output will be steady, because here this pulsating part is removed, DC block here, capacitor block DC, this voltage we get here, so steady DC obtained here. So this is also very important 5-mark question, half wave rectifier or full wave rectifier. And 1 mark question expected is this, okay? Now what you have to do, textbook, all boxed question you have to do it. For example, so this much if you study, 7 mark easily can score. But when you go to textbook, what you have to do, from the first page onwards you have to take. Then you can see in page number, first page if you are taking, there's a question like why, silicon, carbon and germanium are given. Here silicon and germanium are, which one? Semiconductors, while carbon is not semiconductor. I told you the answer. What's that? This one, energy band gap of carbon is more than 3 electron volt, but silicon and germanium 1.1 and 0.7 respectively. They are very small, so they act like a semiconductor. Carbon act like an insulator. This is an important question. It's in a box question, page number 474. It's written in textbook, new textbook. Then I told you this graph, okay? Energy band diagrams I told you, p-n junction diode formation. Then there's a graph given like this, that's in page number 480. There's a question given, graph given like this. See here, like this. Here 1, 2, 3. 1, 2, 3. It is the graph for a diode. So what 1, 2 represent? Here 1 represent before forward biasing, that means before a cell is connected, or we can say unbiased diode. When a small voltage is like 2.2, 1.2, 0.3, I told you potential barrier decreases, then this graph decreases, potential barrier decreases. When higher voltages go 0.5, 0.6, again the depletion barrier decreases. This is the graph it explained. It's in page number 480. Similarly, page number 481, they have shown same way 1 and 2. So this is after reverse biasing, potential barrier increases. This is the main idea of that graph. And in that, I told you page number 481 that reverse biasing, forward biasing, circuit diagram and graph is important. And page number 482, the numerical based on graph 2-3 times I asked in the board. Then half wave rectifier and full wave rectifier is important. And relation of frequencies are also 1 mark frequently asked question. Okay, then you first what you have to study. Take derivation part, note to study it thoroughly and go to any previous year paper and answer all the questions from there. So this is about this chapter. Okay, so next session we will talk about next chapter. Thank you and best wishes for forthcoming exam.